Okay, so this is somewhat different topic, though it does use some of the things I did earlier, but by and large independent. So this is about Markov decision processes are also called controlled Markov chains. So here's the definition. So the standard Markov chain, the definition is that the probability that next state is j given the past say xmm less than or equal to n should be p of j given xn. But here there's some extra variable called zn, which is a control process. So you have two processes. Xn is the state process. I assume it's a finite state chain. And Zn is a control process taking action in another finite state U. And probability that Xn plus 1 equal to J given everything up to time N depends only on Xn and Zn, not on what happened before. And it's given by this function P of J given Xn Zn. So obviously this is a transition probability, so it takes values between 0 and 1 and sums up to 1 over J. So choices of control, the most general is that you can, Zn can depend on Xm and Zm for m strictly less than n, that is all past states and past controls, current state as well, and possibly some randomization, which is independent. I mean, it should be independent of the future. You cannot anticipate the future. That's the primary restriction. So at time n, you can use entire history, including current state, and some independent randomization. So let script n denote this is the time axis, discrete time. And Zn, if Zn is of the form V xn comma n, that means at time n it depends only on xn. It's called a Markov policy or Markov strategy. The policy and strategy are interchangeably used. And then it will be actually the controlled Markov chain will be a Markov chain, though it can be time inhomogeneous because the transition probability can depend on the time. But if Zn is V of xn, so it doesn't depend on n explicitly, then it's called a stationary policy. And so it's a special case of a Markov policy, you just drop the independence. And then the Markov chain will be time homogeneous Markov chain, time independent transition probabilities. Okay. Maybe people are still coming in, I'll just repeat the definitions. So controlled Markov chain is like a Markov chain, but there's this control variable, and the next state probability of the next state taking some value depends only on the current state and the current control. Then this, in general, you allow the control to depend on the entire past, the current state, and some independent randomization. But these two special classes are important. One is this Markov control, where Zn depends only on the current state and current time, and stationary control, where it depends only on the current state. In both cases, it's the control process will be a Markov chain. And here for the Markov policy, it can in general be a time inhomogeneous chain, but for stationary policy, it will be a time homogeneous chain in the sense that transition probabilities are independent of time. So this independent randomization is also actually needed sometimes, and definitely needed in the theory, but even in practice, in some more complicated problems, that's required. And the way you allow sort of accommodate it is to just define. You change your control space from U to PU, which is a space of probability vectors indexed by U. So probability measures on U, and then Markov policy will be some function from state and the current time to PU. So you choose. So the idea is that you at time n you choose control Zn according to the conditional distribution phi given xn, and it's conditionally independent of xm zm for m strictly less than n. So when instead of choosing a Zn is a function of xn or of xn and n, you choose a probability distribution on U. They're called randomized Markov or randomized stationary policies. Any questions about the definitions? I defined controlled Markov chain and general admissible policies, and two classes, or rather four classes: Markov stationary, then randomized Markov, and randomized stationary policies. So again, both for Markov and randomized Markov, it's a time inhomogeneous Markov chain. In stationary or not randomized stationary, it will be time homogeneous Markov chain. And I'll assume that the state, I have already assumed that the state space, the action space from which the control is chosen doesn't depend on the state. You can trivially reduce a general case to this by doing this trick. If U depends on state I, you just take the product as your common control space and redefine transition probabilities P prime of J given I and giving you to dot 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 as P of J given I UI. But even without that, I mean, even without going through this circus, you can just work with UI, it just increases notation. Nothing much changes, but I will stick to a common U. And the objective is to maximize some suitable reward or suitable cost. And generally, it doesn't matter. I mean, mathematically, you can, they're equivalent because, except for one case, which I'll talk about later, because for most classical rewards or reward or cost criteria, you can change cost to reward by putting a minus sign. This is not true for something called risk sensitive control, which I'll talk about later, because the cost goes into exponential. So E of x is not same, not minus of E of minus x. So this is not true there. E raised to x, sorry, E raised to x is not same as minus E raised to minus x. So these are the standard criteria. These are the simplest finite horizon cost. There's some time horizon t, and you minimize some object like this. But this is called a running cost for the prescribed k, and h is the terminal cost. And xt is called the terminal state.
What's the reason to separate it in two parts, terminal separately?
No, this is a actually on the next slide I say that you can absorb h into k also by writing this. Because h is usually kept separate because often it has some separate interpretation, and also because you don't have to put u there. That you would have affected the future which you don't care for. Another extension is you can also have make it dependent on present state and the next state, because by taking one step conditional expression, you can reduce it to this case. This is an important example. Is stochastic shortest path, where you similar object except that capital T is replaced by a random time tau, which is the smallest n such that xn is not in A. So this is called the first exit time from A, or first passage time of A complement. And it is what's called a stopping time. This is an important concept in probability, in the sense that tau less than equal to n depends only on the history till n, or equivalently tau equal to n depends only on the history till n. These two definitions are equivalent for discrete time process, not for continuous. And the intuition is that at time n, if you are at time n, you know whether tau has happened or not. I mean, for example, if it's first time, say, today's temperature, say first time it crosses 32, then by now I know whether it did or not. But last time it crosses 32 today is something I don't know. So that's not a stopping time. And this is if this never happens, then tau is equal to infinity. So it's you allow plus infinity as a value for tau. The infinite horizon discounted cost we saw in the previous lecture also. So alpha is some positive number between 0 and 1 called discount factor, and it ensures, it's of course mathematical convenience, it ensures summability, but it's also popular in things like inventory control and anything that involves money, because they take alpha as 1 by 1 plus r, where r is the interest rate. The intuition being that money spent today is more valuable than money you spend tomorrow. So it naturally arises in sort of commercial type of problems. So this is something, this and the next are something I won't touch. They are more complicated. This is called average cost. So you just take time average. So what makes it difficult is that you take any finite string, it doesn't depend on that. If you drop the first 100 samples, the quantity won't change. That makes it hard. So, and it's popular in communications actually. So this is the kind of thing people in electrical engineering often do, because you are not interested in transients for whatever reason. They're unimportant or fast, and you want to compare possible long-term sort of equilibrium kind of behaviors. So this is in communication networks. This is the favored cost. It has the advantage that because it doesn't matter, depend on the initial condition, assuming positive recurrence, irreducibility, etc. You don't have to remember the initial condition. That's a non-trivial advantage. This is the even more difficult cost, the exponentiated. So what you are trying to minimize is the exponential growth rate. So this kind of, there are two motivations for this. One is, of course, in finance type of applications, this natural compounding effect. So it so this is kind of multiplicative cost, which is natural, but it was also promoted by people because the standard criticism against usual cost criteria there is that they look only at averages. They don't consider the fluctuations. So the average could be optimal, but there could be so much fluctuation that that particular policy is useless. So so people looked at things like some weighted sum of mean plus variance, but that becomes that lacks what's called time consistency. So I'll introduce dynamic programming soon. So that depends on something called principle of time consistency, which means that if I look at the control problem starting from now, and if I look at it from say 10 days from now, 10 days onwards, it's just a similar object, a similar control problem with a different initial condition, etc. But still a similar structure. That goes for a toss if you take mean plus variance, mean plus. So, I mean, in economics, actually, it was introduced long back, kind of mean variance trade-offs, but it's not convenient. So this was introduced because here you have some kind of multiplicative sort of structure which you can exploit for dynamic programming. But now even this has is falling out of favor, and people are using there's some axiomatically justified risk measures like CVAR and so on. Okay, so let me denote by P sub U the stochastic matrix whose ijth element is Pg I comma Ui. So U is the entire vector of controls. And for a stationary policy V, the transition probability is Pj given I comma Vi. I will just write P sub V. Okay, so it's either a fixed control or a stationary policy. So similarly, I will use a subscript for denoting randomized stationary policies. So this is the standard way, not the only way, but standard way of approaching control problems. So this is a verbal statement. The minimum cost to go at a given stage is the minimum of the expected sum of the immediate cost and the minimum cost to go from the next stage. Okay. So you look at what you have to pay plus what you expect to pay tomorrow onwards. Minimum of that sum is what you expect to pay now. So this actually is, taught in basic algorithms course in computer science for the multi-stage problem. So you want to go from some initial stages to final stages, and you have several in between. And you can draw as many arrows as you want. And the idea is that there's some cost or reward associated with this, and cost associated with these links. So you start at each of them. So look at this cost. To this you assign a node. So costs are assigned only to final nodes and to links. And these are the initial nodes. Suppose you start without loss of generality. Suppose you start one particular one, because you can always handle them individually. So you assign some number, so 10, suppose this is 5, then you assign 15 to this. This is 7, you assign 17 to this. So suppose this is 3. Oh, so, no, this is not true. This is okay. This is also okay. But here what happens is now I would get 18 here, 7 here. Suppose this is, I assigned 5 here, 8 here, so 13 here, 2 here, so 15 here, and say 1 here. So here what I have to do is to, if I go this way, it's 19, this way it's 17, this way would be, I have not put anything here, so 7 say 12. So it would be the 12, 17 and 19. So you take the minimum and put that here, so 12. So just this idea pushed more to more abstract setups is what you have here. So finite horizon cost is repeated the definition. Define what's called value function, which is a function of t and I, time and the present state. And Vt of I is the minimum cost to go if you start at t, at state I. So t is my current time, I is the current state, and the minimum of what's left to go. The minimum is all admissible controls. The dynamic programming principle gives you anyway the first. This is not a proof, incidentally, because I'm using this follows from dynamic programming principle, which is minimum of current cost, expected value of current cost plus minimum cost from next time onwards. I have not proved dynamic programming principle. I just stated it, but let's use that here. And then this is, I can take one-step conditional expectation. I get this, the same as this. And then since I'm minimizing over, I know that xt is I and I'm minimizing over zt, so I can treat zt as a variable u. I get this equation. And the terminal condition is h. I already said this. Is this clear? So this is dynamic programming equation. Minimum cost to go is minimum of expected value of current cost plus minimum cost to go from next time onwards. Take one-step conditional expectation, which is this. And xt is I, and I'm minimizing over zt now because everything else is buried here. Future controls are buried here, so only the current control matters, and it gives me this deterministic equation. So this is called a dynamic programming equation or finite horizon problem. And what you do is basically you just do backward recursion. Start with terminal condition h at capital T. T, plug it in here for t plus 1 equal to capital T, and you get v at t minus 1, and keep going back till you come to the beginning. And the interesting thing is that the minimizer is the optimal policy. That's more or less clear from this example. So once you solve it, you are also told the optimal policy. So if I have solved for v, then any zt which is in the minimizer of this object will be the optimal choice. And you can see that because this depends only on xt and t, you will get some Markov policy vt comma I as a optimal choice, and it's if and only if the Markov policy vta is optimal, if and only if you can satisfy this. Okay. So this is the simplest problem. It becomes more complicated. Okay, so yeah, I already said this. So the dynamic programming equation is you can solve by backward recursion starting from the terminal condition, and then having solved it, find the minimizer by performing the explicit minimization in the equation. So that gives you the minimizer will depend on t and I, say vt comma I. Then the control choice at time t is zt equal to vt comma xt. And this can be pushed to slightly more general things. It's just notationally more intensive, but I can put this exponentiated factor there, and it will give me this. And if I take c to be this not c, this should have been e raised to c to be alpha, then it becomes a discounted, finite horizon discounted cost. Okay, the infinite horizon discounted cost is this, which I had mentioned earlier. And the problem here is that there's no terminal time. It goes on forever. You cannot do backward recursion. You cannot start at infinity. So, but the advantage is that now it doesn't, unless I explicitly put an argument t inside k, it doesn't depend on time. So if I start at time, start today and look into the infinite future, and start tomorrow and look into the infinite future, the cost is the same. So the value function will depend only on x. And the dynamic, so this is the defined value function as a function of state alone, infimum of the overall admissible controls of the infinite horizon discounted cost. And then using dynamic programming equation, you can show that it satisfies this. So minimum over u of current cost plus your future is discounted. So after one step, you discount it by alpha, and one step conditional expectation. You get back the same v. So it's kind of self-referential. I mean, it's not, earlier I had v I comma t and I comma t plus 1 here. Now it's the same v. Anyway, okay, so this just shows that this equation, so this is, it's not obvious that it has a unique solution. It does. This one brute force way, this is a simpler way also, but this is kind of more intuitive. If I minimize and I get some zt of vxt, I plug it in there. If I plug it, suppose the minimum is at, what did I call it? V. If the minimum is at vi, I can plug it u equal to vi here and get an equality. And then by iterating the equality, I get that vx0 is just iterated and let t goes to infinity, it's the cost. If I take some other control where instead of equality or inequality, you get this. And then if suppose x naught was I, this itself shows you that vi is the minimum cost to go. So this is the unique solution. And the stationary policy zt, which is optimal for any initial condition if and only if it minimizes this object. So if you solve the dynamic programming equation for v, you solve the discounted cost problem. So there are, see, this is so this is not solvable by backward regression. So there, so this is something important because I'll use it in reinforcement learning. So that three classes of algorithms broadly. This is called value iteration, and it just starts with some value iteration because we are trying to estimate the value function. You start with some guess v naught, and keep doing this iteration. Plug current guess there, and then perform the minimization. And if v is the solution, you can, I mean, this kind of routine calculation. Suppose that see how far vn plus 1 I is from vi. Just use the dynamic programming equation, plug in the right-hand side here. Then mod of min, so this is a universal fact, mod of min dot 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 minus min dot 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 is less than equal to max minus dot dot dot. And if I put max here, also the same thing is true. If I pull the max outside, get rid of the min and put a max outside, then the k cancels, alpha comes out, and you have this. Now, because this is a transition probability, I can the max. I can pull the max inside by putting inequality, and sum over g of iu is 1, so that goes away, and you have this. So then I take max over I on the left-hand side. I find that this max norm between Vn plus Vn and Vi is going to 0 exponentially. So it's an exponentially fast algorithm. Another any questions about this?
U is a function of I and
No, U depends only on I.
I and only I.
Yeah, because the dynamics is not, I mean, the discounted cost doesn't change, it doesn't depend on when you start. So there's another scheme called policy iteration, which starts iterates in the policy space. So you start with some guess for stationary optimal policy, and at time n, Vn is your current guess, then you perform two steps. One is that just plug in Vn. So instead of by the same argument with which I came up with dynamic programming, you get this equation. So suppose you pretend that there's only one controller available, namely Vn, you will get this equation by dynamic programming argument. And this is linear, so you just solve this linear system. Okay, and that gives you Vn with the value function corresponding to Vn. That means if you use Vn, that would be the value. And then Vn plus 1 is obtained by minimizing this. And this will be less than equal to this. So in particular, it tells you okay, you keep iterating these two steps till you get equality here, and then you stop. And then Vn is optimal. Because if there's equality, then under Vn, the dynamic programming equation holds. And therefore, Vn is optimal. I mean, dynamic programming equation holds with equality under Vn. Whenever Vn is equal to Vn plus 1. That you can check it from this. So if this is equality, then this has already attained the minimum here. Finite. Yeah. There are, I'm sticking to finite, but because my aim is to go to reinforcement learning, this also works for much more general spaces. Of course, you need more conditions.
Because we have that minimum over u, right? That minimum has to exist.
No, that U is generally, U is less of a problem. The state space being countable is a bigger problem. The control space is usually nice. The state space, actually for discounted problem, it's not a problem. It's not much of an.
Minimizer will always exist for that.
No, it depends. If you have a compact control space, that's enough.
How do you make it compact?
No, compact is a close bounded. For example, in queuing, it's typically compact. You just sort of send block or send kind of. Very often, at least in a lot of engineering programs, it's 0 or 1. But that doesn't have to be the case. But in case it's not compact, then the dynamic programming equation holds with infimum instead of minimum. Then you will get only epsilon optimal. But again, many problems when it is not compact, typically you will have a penalty which penalizes the control as well. So again, for example, if xn plus 1 is xn minus un plus some function, say fxn minus un plus some noise, that's a typical case in queuing problems, then you typically put a quadratic penalty on un also, so norm un square, right? Because it usually means energy, it costs something to transmit. Yeah, so that makes anything with large Q suboptimal. Yeah, so you can show that this is also easily checked that at each till Vn becomes equal to Vn plus 1, there will be a strict decrease in at least one state. I mean, it's a more or less tautology. If Vn is not equal to Vn plus 1, you are going for something is changing and you are doing minimization. So Vni is strictly bigger than Vn plus 1i in at least one state. So what you can argue is that the cost is decreasing for at least one initial condition. And then because I'm in a finite, here this is where finite state helps. So it's a very large, if I consider stationary policy, there are functions from a finite set to finite set. So the set of stationary policies itself is a finite set, though extremely large, but still finite. So this thing has to converge after to an optimal policy in finite time, which can be exponentially large in the problem parameters, but still finite. If you drop finiteness assumption, then the convergence is asymptotic. This doesn't seem to be working with. Yeah. If you have a continuum, for example, or even countable, then you need to approximate. It will be approximately optimal. I mean, theoretically, you can show that they converge, but the thing is that you cannot work with infinite vectors. Even, I mean, these are extended to more general state spaces also, not just discrete. So if you iterate in some Banach space or something, you can prove convergence, but if you were to implement the algorithm, finally you'll have to approximate by some finite. There are various kinds of approximations. I mean, discretization is not the only one. When I talk of RL, I'll talk about other ones. Where is this gentleman? This doesn't seem to be working. Oh, it worked. Oh, now it seemed to work. But I think he has put down the older slide. I told him to put the one I gave yesterday. This is the last slide of this particular deck. What I did was to merge the two and send it. So let us continue. Because the limit may not be defined. This is the worst case. Same in average cost also. I mean, one can show that for under optimal choice, it will be limit. But a priori, you can't assume that. So you show that optimum is attained for a stationary Markov policy, and then you can show that it's a limit. So this is as I said, this is somewhat not, it's a multiplicative dynamic programming. So for example, if I fix a control, then all dynamic programming equations for everything else will become linear equations. So the dynamic programming equation in some sense an envelope of linear systems. Here, even for a fixed control, it's not a linear equation. It becomes an eigenvalue problem. The eigenvalue is also an unknown, as is the eigenvector, so it's non-linear already. And the dynamic programming equation becomes multiplicative. Okay, sorry about that. I copied MDP into RL rather than RL into MDP. Okay, so a brief introduction to machine learning, basically. This probably many of you know already. So there are three broad categories. It's kind of loose terminology. We don't be very rigid about it. But supervised learning, the idea is that you get some precise feedback about your performance. For example, in the neural network training, the gradient is given to you. So one thinks of a teacher who's telling you how well you are doing. In unsupervised learning, there's no feedback at all. Sort of you self-organize. So clustering is one standard example. So you can think of skipping a rope or riding a skateboard, which basically you have to learn yourself. And reinforcement learning is supposedly between the two of them. So you get some feedback, which is called evaluative feedback. That means you get some reward or cost, possibly noisy. I have not taken noisy rewards, but that can be easily accommodated. And think of your parents or spouse just making a face, scolding you or smiling at you without giving you any precise reason why. And there's a long history which is very interesting actually. This Thorndike was, even in his student days in Harvard, apparently used to have all kinds of exotic animals in his room, and that used to cause a lot of problem in the dorm. But this William James, who was a psychologist, he kind of was his patron, so to say, and he helped him find some other apartment where he could continue with his experiments with animals, and supported him in general. And later on, of course, so actually, I mean, this machine learning or computer science are latecomers to this field. All the early work was done by people trying to understand animal behavior. And then in mid around 50s or so, the psychologist, I think Mustiler was a statistician, Bush was a psychologist, and statisticians, etc., got interested in it. And there are, of course, parallels with classical engineering adaptive control mechanisms, but it's significantly different from them. So the classical adaptive control in engineering is broadly these two things. In self-tuning control, you kind of estimate a parameter and just plug it into your control policy as though it is the correct parameter. So you may be running some maximum likelihood or Bayesian scheme to estimate. You have a model, you estimate the problem parameter and treat it as a true parameter and come up with a control scheme. Here, what you do is you have a model, you have the true system, you feed some control, and you get some outputs from the true system and the model. You consider the difference and use that error to tune the model. And there was also something called direct adaptive control, which was Sipkin and his students in the Soviet Union, and it was followed up by these people. Narendra was in Yale and Tatachar was in Indian Institute of Science. This is based on learning automata, and that is closer to RL in spirit in some sense. Sort of both. They also use stochastic approximation, but yeah, but there are some differences also. But that's compared to the previous two categories, this is the closest to the modern reinforcement learning. And the current wave of whatever ideas came from a lot of cognitive scientists, particularly there are two people who did a lot, and much before actually it became popular. There is Richard Sutton and Andrew Barto in UMass Amherst, and they are of course trying to model the brain. And there was this interesting experiment by a person called Schultz, where he had some data from rats, which he could not explain. So he was the usual, give it some food and see how the amount of dopamine released and so on. And it didn't match what his model suggested. So he put the data in the open, and this person called Peter Dayan, who was one of the pioneers in RL, and his colleague Montague, when they saw the data, they realized that the rats were doing what's called temporal difference learning. If there's enough time, I will come to that. So they tried to fit the data to the reinforcement learning algorithm, and it fitted. So that was one major concrete evidence that it was not nonsense. But of course, then the engineers picked it up for other reasons like robotics, application of robotics, and so on. And one reason this should not be underestimated or understated. Why so much delay from the ideas to actual use? The thing is that they're not small, short and sweet algorithms. Something like intelligent brute force needs a lot of computing power, and that became possible only later. So now it's possible to use this. When the people started their work, it was not that easy to implement them or that cheap. So broadly, then, I mean, if you mathematically speaking, you can think of it like some iterative scheme for MDPs and take some stochastic approximation version of it to make it data driven. So you replace averages or conditional averages by incremental iterates for averaging. So I already talked about stochastic approximation in a previous lecture. So let me just recall. So the Robbins-Monroe scheme for finding the zeros of expected value of, so you have Hx, you want to solve this, and what you have is Hx plus noise. So the scheme was xn plus 1 is xn plus an hxn. So this is noisy measurement. Okay. So what this does is to basically average out the noise, and the same thing you try to do here. So it's kind of, you can think of it as something between purely probabilistic schemes like MCMC and purely numerical schemes, the trade-off is the sort of, okay, we will come to the next slide. No. The trade-off is that basically you try to get some kind of sweet point between the two. So there's part numerics, part randomness. So typically the pure numerical schemes like value iteration, etc., will be for large chains will be extremely expensive. So here you reduce that by just replacing part of it by simulation. So by policy, okay, many of the schemes are for policy evaluation. You fix the policy and evaluate the performance. So there, this statement is more accurate, not for optimization. So let me start with the first one. At least I hope to. This is a sort of easy to explain also. Hope to finish this. I've done this in much more detail. So we have the discounted value function, and we have the dynamic programming. Now it's of the form v equal to fv. It's a fixed point equation. You are trying to solve a fixed point equation. And if it's nonlinear, there's a conditional expectation with respect to p, which is inside the nonlinearity. So that's the problem. So suppose I just wanted to replace this by a policy value iteration, say. Okay. So Q-learning actually is inspired by value iteration. So if I start to replace write value iteration vn plus 1 equal to blah blah vn, then to make a stochastic approximation, I have to get rid of the conditional average and replace it by some sample evaluation at some specific sample. But then there's a problem because then the averaging is inside a nonlinearity. So you can't do that because expected value of minimum is not minimum value of expectation. So what you do is, so I already said this. So what you do is you look at, actually, well, let's go back to the, so this object inside, this object is what I call Q value. So define Q value to be that. Then Vi is just minimum over U of Qi comma U. So Q satisfies its own dynamic programming equation, the Q value. But now the minimum is inside the average. It's still a fixed point equation, Q equal to GQ. So if I call this, I can string these out into a vector and write it as Q equal to GQ for a suitable function G, where the average is outside the minimization. So here's the G. And then you can write you can think of a Q value iteration. This will also converge, of course. It's the same argument. It's kind of fixed point iteration for a contraction map. And see, the advantage is, okay, I have not yet come to the RL algorithm, but the advantage of learning Q is that once you have Q, you don't have to know anything else. So if you go back to the dynamic programming equation, when I do the minimization over U, the quantity being minimized involves Pj given I comma U. You need to know the transition probabilities. Okay. So there are two reasons why this facilitates reinforcement learning. One is that the averaging is outside the nonlinearity, namely minimization. So I can replace it by a stochastic approximation version. Secondly, I don't have to know P. If I have some simulator or some actual data coming in, that's good enough. I just once I find Q I comma U, I just minimize that over U. Okay, but we have increased the dimensionality from the dimension of S to dimension of S comma across times dimension of U, which is can be quite large. So you are losing something, but then after this, I mean, this is the first building block. What people do is to approximate this. I think that was Supratim's question. Later on, I'll talk about some approximation schemes. So you take the usual stochastic approximation algorithm, and the ith component of the iteration. So now your components are labeled by I comma U. So I comma U component. You just take a convex combination of the previous iterate plus this right-hand side suggested by the Q dynamic programming equation, and just collect together the n terms, you get this. Where cyan are, I mean, this is, I am going to change it further. Right now, cyan are independent S-valued random variables generated with this transient probability. So I'm assuming that there's some gadget which throws out given I comma u, it will spit out sign I comma u with desired transition probability. So this is the synchronous version, because I am updating all components at the same time. Okay, but usually you are forced to use asynchronous version. Okay, so let me just repeat what I did. I replaced the conditional average by an variation at a simulated random variable with precisely the same transition probability, and then made the update incremental. So I replaced the candidate update by a convex combination of the previous iterate and the correction term with these weights. So you make see, without this, you just plug in the right hand side with a simulated random variable. It will be like a random walk, more or less. Oh, sorry, I think yeah, it's same as this, I think. Yeah, I forgot to change that notation there. So it becomes a fixed point stochastic approximation algorithm, which we have seen already in last lecture. So what I do is just subtract. So this is the object I have. This is this conditional expression. So after you subtract the conditional expression, it's uncorrelated with the past. Okay, I had this, my model for stochastic approximation was, this was some random variables which were uncorrelated with the past. Okay. They're called martingale difference sequences. Some of you may be familiar with that. So it's a martingale difference noise, and then I am left with G, just this G is this function of. So I've written X as a random variable instead of Q. Sorry, X as a variable instead of Q. Okay, so the ODE is Q dot equal to GQT minus QT if you take the ODE approach, and this is a fixed point. This is a contraction. You can check it the same way we checked it for evaluated. I mean, just a standard argument to just pull the K cancels, pull the min outside as a max, and I just cancelled the K and then pull the alpha out, and I mean, it's a routine calculation. You get a contraction, and I already proved that, pointed out that for if your x dot equal to fx minus x and f is a contraction, then it converges to the unique fixed point, and therefore the algorithm will converge almost surely to the so by the contraction mapping theorem, G as a unique fixed point, which is the solution actually you want, the Q value you are looking for. So the ODE trajectory will converge to Q, and therefore the iterates will converge to Q almost surely. You need to check this condition. This is all, but for Q learning, it's free, because you can see that each Q learning iterate is a convex combination of the previous iterate and something bounded. So this is never an issue. In some other algorithms, you have to ensure stability. Now this can be generated by a simulator or whatever. So this is often done. I mean, it looks wild, but the RL people do it. They have the buffer a lot of data and sample from accumulated data. If I just in the data, if I have a large amount of data and I just pick a random, so they have this triplets I, U, J of past transitions. And suppose I pick some random triplet by just giving I and U as input, then the J will be approximately with this probability, because the data is generated from the Markov chain, and it would naturally be satisfy this. And a more, I mean, I shouldn't say more common, but very often you have a single run of a real or simulated Markov chain. Just run this. That means you get only one, you are only observe only one state at a time, and one state control pair at a time. So more commonly used algorithm is this. This is asynchronous, because this is indicator xn equal to I, zn equal to u. So when the process is at I and you use u, you update the ith component and don't touch the rest. So this is an asynchronous version of this. You will get some stuff sitting here, but that doesn't affect the convergence as long as everything is sampled often enough. So this also I had mentioned. So for infinity contractions, this is enough for convergence. And the reason is that if you have a, so what I'll get is I minus lambda times identity plus lambda times f. So even if I put t here, doesn't matter. So if f is an infinity norm contraction, fx minus fy infinity less, then this will, if this satisfies a condition like that, this will continue to be an infinity norm contraction uniformly in t as long as the relative frequencies of sampling remain bounded away from 0. So it works. So in the off policy case, this is a jargon from RL literature. That means you are simulating on a computer. Then actually it doesn't matter what xn and zn you choose as long as that is true, as long as you are sampling everything frequently. You can even choose xn comma zn IID. I mean, people don't do that. They'll use something more, whatever is convenient for them. But there's a lot of leeway in how you choose how you sample. But if you're actually in the on policy case, means you're actually controlling something using this, then you have to be careful because you cannot experiment arbitrarily. And then it's common to use what's called epsilon greedy. So take the current estimate of Q. The minimizer is your current estimate of the optimal policy. You play that with probability 1 minus epsilon, and with epsilon you use some randomization. And people also worry about how to decrease this epsilon to 0 to get asymptotic optimality and so on. But that's still, and also this is not a, I think this is not a complete solution in every situation because there can be problems. So they have given 2 examples. There's something called safe reinforcement learning, where if there are some mistakes can be disastrous. This is particularly true in autonomous vehicles. You make one wrong guess, you can crash. And there are well-known problems with autonomous vehicles because they're vision-based and they look at the wrong thing. For example, I mean, in some experiment, they found that the car focused on some billboard instead of a pedestrian crossing the road. And that was an experiment. So it was a dummy, not a real man. But otherwise, they could have killed somebody. So that kind of thing you have to worry about. So you cannot just try out any policy just to train it. Because so basically this is an active area and we will try various things such as some emergency control that you should detect that you are going out of bounds and do something drastic. Another issue, another major issue, particularly robotics being a major application area, is many times the reward is often is delayed. And for example, you want to train the robot to say take this water bottle outside and put it into garbage can. The robot starts here, and you will know that whether it has succeeded or not. It's a full Markov chain from here to the garbage can, but you will know whether it worked or not only at the end. So there are all such problems which people are still struggling with, and so this is kind of this also I already mentioned. This is what typically approximates Q by a parameterized function family. I will come to that a little. I don't have too much time. So I'll very briefly mention this. There's something in some. Many times your dynamics is like this. The effect of control and effect of noise are separated. Queuing theory is one example. See, this is a queuing example. And then just by interchanging f and g, so if I can define, I can call this g of xn zn as yn, and then I get another process. Okay, and then you can sort of write yn as g xn zn. There's a definition anyway. Xn plus 1 is f of yn zn plus 1. Then you have this Markov chain x0, y0, x1, y1, etc. If you write the dynamic programming equation for xn, you get the old one with the usual problems. there's a mistake here. There should have been conditional expectation with respect to something, I think. Yeah, there should have been this conditional expectation somewhere. No, it's okay. Sorry, it's correct. Look, I'm alternating between the two. So if I write for this alternating chain, I get this equation. I have used different letters for the y and for the x chain. But now if I can either plug in w here and get something for v, I will get back my old equation. But if I plug in v and take v and plug it into w, I get an equation for w where the averaging has come outside. So the yn is called a post-decision state, and you may not always have this convenience, but when it does, it helps. So the other class of algorithm, this is modeled after, inspired by policy iteration, and it's easy to describe. So this is, sorry. So this policy iteration, I can replace policy iteration by stochastic approximation, which will be fine if the control was fixed, because then it's a linear stochastic approximation. The problem was the minimization. But then what you do here, use two timescale stochastic approximation. Use a slower timescale to update the policy. It's convenient to update a randomized policy because the probability simplex is an easier object to work with, being continuous variable rather than a collection of discrete finite set. So what one does is work in this probability simplex and write some iteration. I have given one iteration here, which I'm going to skip because this analysis is actually quite intricate. Use this Gibbsian formulation and then tweak. Of course, in principle, I should allow for beta to be arbitrarily real, but I'm constraining it to a large set so that I will get only epsilon optimal. And then run some algorithm like this. So this choice of algorithm is not unique. There are multiple choices for the minimization part. But basically you run value iteration, a linear stochastic approximation for the value, and for the policy evaluation, you do one of the minimization routines on a slower time scale. So because on a slower time scale, you can use the two time scale argument to pretend that it's sort of quasi-linear for analyzing the value iteration and do the joint convergence. So what you can show is that if phi n was the policy indexed by phi n was this policy, one can show that this value iteration sees the policy as quasi-static, so it will track the optimal, it will track the value for phi n, and then you plug in phi n for the original algorithm. So this is probably the worst of these slides. I'll skip it completely. You can show that it converges to a near optimal policy. Okay, this I already said. Now TD0 is a policy evaluation scheme. One of the earliest schemes is basically this Sutton, Bartow, and Anderson. And this is policy evaluation. That means you fix policy and evaluate it. And so, because I have fixed the policy, I ignore it. I just write it as an ordinary transition probability. This is the dynamic programming equation. It's a linear equation. And what I do is I approximate V by some linear combination of some basis vector phi m, and then try to, so phi m functions are fixed. This is one standard approximation. You fix phi m and learn only Rn. Then you are approximating V by phi r, so you hope that this approximate equality holds, which it may not. So you look for a fixed point. So pi is a projection on the range of, phi, this capital phi is the matrix formed by whose columns are these vectors phi, small phi, and it's full rank because these are chosen to be linearly independent. And you are trying to solve this, you want approximate equality. So what you do instead is, that may not hold actually. This right hand side may not be in the range of the capital phi. So you solve this fixed point equation. Pi is a projection. And it's convenient to, since you are working with a fixed policy, take the corresponding stationary distribution, use this weighted L2 norm. It's convenient to do this. And then you can show that the projection amounts to this operator. You also see this is important actually in the analysis. You also see that this is a non-expansive map. The operation of the transition probability is non-expansive with respect to the weighted L2 norm. Then this becomes a contraction with respect to weighted L2 norm. And therefore, the solution to that equation, that fixed point equation I wrote is unique. Now, what they did is to define this thing called temporal difference. This came from the cognitive science side of them. So this is, so in the Schultz experiment, what they found that the mice, the dopamine release in the brain of the mice was explained by the temporal difference. The current reward and their expectation of the next reward. And then, of course, the algorithm is to, they came up with this algorithm. It's not obvious actually, but it works. And I'll skip the, what happens is that it ends up being sort of like, actually, I want to emphasize this because it's not a gradient system. If I define psi r prime like this, where if at one I distinguish between this future, the r I see in future, which is under the conditional expectation, and the current r, okay, then it's a gradient. It ends up being gradient descent with respect to only the first one. So if I have some fx comma y, and sorry, if I see this problem will arise again. If I have fx comma y and I look at fx comma x, I have only one variable. I want to minimize this. What I would do is to write gradient with respect to the both occurrences. If I write gradient only with respect to the first, so if I write minus grad f grad 1, say with respect to this occurrence, there's no reason at all why this should converge, why the gradient descent should converge. But in this case, it does. This is a very special case, and yeah, so you are so the way they think is that the first x is your current guess, and r is the current iterate, and r prime is the target you are trying to chase. But the target is itself equals the current guess here, and you get this limiting ODE for which this miraculously this Lyapunov function works, and therefore it will converge to the correct. So this is a provably correct algorithm. And anyway, using the what? No, but this is just a proof of stability. I'm not using it in the algorithm. This just proves that it doesn't blow up. Sorry, it proves that it converges and it doesn't blow up. Needs another, the standard test which one test, not standard, but one test which I described in my previous lectures applied directly. So this is the TD lambda as another iterate. I'm not going to talk about it. Sort of more computation, but it improves performance. You kind of what they call credit assignment. You whatever you see, you assign credit to some past iterates also, or you account for some previous iterates as well, not just to present value of xn, but xn minus 1, xn minus 2. It's a different algorithm. It's a family of algorithms for lambda belonging to the interval 0, 1. TD0 is simple to analyze, so I analyzed it. I'm not going to analyze. Computation is more, but it improves performance. I mean, it will fluctuate less, for example. Yeah, okay, so yeah, so this is quite flexible because I started with a finite state space, but since phi is a function of state and you just plug in the state, you can use it for continuous valued state space as well. The algorithm doesn't change. In fact, if it's partially observed, you can plug in observe. See, if you have a Markov chain xn and yn is some partial observation of xn comma yn is also a Markov chain. You can think of that as your Markov chain, and just take functions of yn. It's legitimate. And depending on how good the observations are, the performance may vary. But this can cover continuous state space and partial observations in principle. It is used for continuous state space also. It doesn't matter. You are finally working manipulating only the coefficients, and it's linear, so you can use it as I said, actor critic. The first iterate, the value iterate is sort of like linear because the control is moving slowly. So you can replace it by TD lambda, which is how actor critic is usually done. You don't run the full value iteration, but TD lambda. Okay, so this is a very popular algorithm, one of the earliest. This one is actually maybe I'll skip. This is sort of like it tries to minimize a different objective, and you end up getting some iterate where you have this inverse. It has the flavor of a Newton kind of thing, so it accounts for more structure and therefore is faster, but per iterate computation is significantly more. It's not as popular as the other ones. So you have this algorithm, and I just want to mention one fact that this inverse has to be computed recursively. There's something called Sherman-Morrison formula. You start with some delta times identity to avoid, to ensure invertibility, and then see the way you need to update the inverse is you make rank 1 corrections to the matrix. And there's a formula to find inverse of C plus UV transpose given the inverse of C. There's a extension called Sherman-Morrison-Woodbury formula, which allows for low rank corrections, not necessarily rank 1, but this is for this particular purpose, this is enough. The limiting ODE is some stable linear ODE, so that's not a problem. Okay, policy gradient methods are extremely useful, extremely popular also. So what you do is you again parameterize everything, and then so basically what I'm parameterizing is the transition probability, and therefore V and sorry, I forgot to mention one important thing. I'm doing this for average cost and not for discounted. So this is the average cost equation. There's no discount factor, and there's another unknown variable which turns out to be the optimal cost. The reason I'm doing this that it's more elegant here. It was slightly messier for discount. Though it has been, I think it was first done for discounted cost, but this is nicer to show in a few slides. So this is the DP, the constant policy equation, Dunning-Kruger equation, where K theta is the Q theta is the randomized policy, and parameterized by theta, and there is a corresponding cost averaged out over the control, and similarly this is the corresponding transition probability averaged out over the control. And then what you do is you just differentiate the whole thing all through on both sides, and then use for the fact that pi theta is the stationary distribution which satisfies this and this expression, and you just go through the algebra, which is not particularly hard. You get explicit expression for the gradient. So the idea behind policy gradient is to get explicit expression for gradient with respect to parameter, and then do gradient descent. So you parameterize the policy, not the value function, but policy itself. You may parameterize the value function also, because that will come soon. But mainly you take a parameter for a form of policy, and you have an explicit expression which does involve value function. So you need value function. You do the gradient descent. This is the kind of what it amounts to, and it's gradient descent, so it will converge to a local minimum. But you need need the value function, so that will have to be estimated on a faster time scale using the TD lambda or any scheme you like. Okay. So this is actually the most popular method, because lot of so this is the most popular paradigm also, because the linear function approximations are the only thing for which are provably correct for at least the policy evaluation case. Otherwise, you cannot show correctness of these algorithms. But now everybody is using deep neural networks, etc., which are not linear. So what one does is to define this error between the right-hand side and the left-hand side of the Bellman equation, the dynamic programming equation. And this is called Bellman error, and you try to minimize this. So this was, so you write this gradient, and there are multiple problems. One is that the two conditional expectations, the product of conditional expression, which is not same as conditional expectation of product. When you do stochastic approximation, you can hope to get one conditional expression, but now there's a product of conditional expectations. And if you do this, this was proposed by a man called Baird long back, and he plugged in the original thing and simulated another random variable with the same probability, the same transition probability here. This kind of brute force, this is called double sampling idea. So to get conditional expectation of, to replace conditional expectation of product in place of product of conditional by product of conditional expectation. So this will in principle work, but it's somewhat clumsy. So there are two things people do. So okay, so you can embed it in a larger family of algorithm, but let me look at this. This is the two sampling version of it, but I'm going to get rid of this as well. If I do this, okay, so I use basically Q, consider the QDP, the dynamic programming equation of Q value, and try to minimize the corresponding Bellman error. I'll get this two sample version, but I want to change that as well. Rather, people have changed that as well. So what you do is mimic that idea. Treat the second occurrence as a target and don't touch it. Don't take gradient with respect to that. Then life becomes easier. There's only one gradient. There's only one conditional expectation, and you get this. This is called a DQ and deep Q network. I mean, the nonlinearity uses deep network and deep network for Q learning, and this is a very popular algorithm. So the two important things is that I'm freezing this, not taking gradient with respect to theta prime n. What they do is to keep theta prime n fixed over a certain window and then set theta prime n equal to theta n. So the target is kept fixed for a while, not for too long, and then every periodically they equate theta prime n to the current theta n. Now these variants where which I mentioned are slower. Okay, this is still the most popular. It is not provably correct. So for the linear case, the TD0, I could produce a Lyapunov function which worked, that half norm r minus r star square. This is not provably correct. It's known it can diverge, but it works well in practice and people use it. Okay, so there are some advantages. They also do something called experience replay. There are a lot of ad hoc tweaks which are used. The first bracket, the long term, you actually you have buffered data. You take data from there and do an averaging of that already. That helps. So you have averaged out the first term, so you see already the conditional expectation, and then do this kind of ad hoc scheme. So this came out of Google with a, I remember the first name of the list because it has exotic spelling. I don't know how to pronounce it. Et al is the everybody else, quite a few. And it's kind of very the current rock star of this area, but the theory is still waiting. Yeah, I mean that's for theoretical purposes. Since this is not provably correct, one can probably use. In many cases, people use constant step size. Frankly, if you want to prove almost sure convergence, you use decreasing step size. But unless it's a stationary environment, it's not good. Generally, if it's a slowly varying environment, people will use constant step size. Yeah, so experience replay is what you average over past, and there are various people selling points are it reduces variance, reduces effect of anomalous transition, occasional bizarre behavior is not given too much importance. Then, all these things. This is I took from some somebody else's work which promotes this thing. So yeah. Number 5 is important. It's better suited for delayed rewards, like robot walking and doing something at the end. Yeah, so here they do express AAA only for the first product term. And this is the good median time. This is another algorithm by Sean Mine and his team. I think a couple of others. He called it ZapQ learning, and it's quite long. Just want to point out some analogies. One is that it has the Newtonian kind of object, which is like that LSP algorithm, which I did not describe. That's due to Bursakas and Dedich. And there was this matrix inverse in front, and that improves the convergence behavior at the cost of additional per iterate computation. Something similar here, but if you just consider a number of steps, this converges very fast. So this is probably the last slide. Yeah, let's stop here. Anyway, I should mention that there's focus here is on games. That's a wide open area. For zero sum, at least in the vanilla case, you can replace max by min max or min by min max. That will work, definitely for discounted. But otherwise, the multi-agent and general non-cooperative, not too much. I mean, there things are happening I get Google alerts every week for something multi-agent Q learning or whatever, but still it's a hot area, but probably will remain so for a while.
Questions? So I had a couple of questions. So there are these many different algorithms that you mentioned, Q learning, TD0, TD lambda, then ZapQ, something like that. So when are these different algorithms most suitable? What kind of situation should we apply? I mean, if you want to apply a particular kind of algorithm, how do you select which one is the best or the most suitable?
Actually, the Q learning and actor critic which I described are vanilla versions, in the sense that typically for you cannot use them for very large problems, because the theory is nice. We can prove convergence and convergence rates and whatnot, but because the state space can be very large, which is typically the case here. And so all these approximation architectures are used. Currently, mostly policy gradient, some either DQN or some other variant. So you come up with, you take parameterized policies and then update the parameter. Most of the time it will be parameterized or Bellman error minimization. And so the various variants keep being published at various speed up. People keep coming up with clever tricks to speed up or cut down computation and so on. For example, sometimes they work with batches instead of single samples. That improves things a lot. Enormous literature on just fine-tuning the specifics. I should also mention that this chess beating programs, etc. So the good old days, basically, the chess, of course, you're a better player if you can see into future. So with exponentially growing possibilities, the number of steps you can see into more steps you can see into future is better for you. So in a sense, the success of the Deep Blue, etc. I don't know whether Deep Blue does exactly that, but I think it was not doing anything. It was basically computing possible trajectories, which can compute much better than Spassky. That's not a surprise. But the current, like this AlphaGo, etc., they are using reinforcement learning, and they are also being trained on past data, and then they play against themselves, and that seems to be doing wonders. So it's not completely understood. RL actually, because it's also interfaces with many other sciences, cognitive science, this and that. There's still a lot of gray areas which are not understood at all.
I am not getting any reward. Today, like now I'm playing this move. How are they saying that this is a good move or this is a...
No, the reward will be typically designed by the engineer. At least see robotics. The robot doesn't know that what happens at the end. The robot doesn't know what algorithm. The robot is programmed, but the engineer would have trained the robot using some say reward 100 if he places the bottle correctly and 0 if he or minus 100 if he doesn't.
But the robot thing is like it has a specific path and a specific task.
Yeah.
But when I'm playing chess against someone else, my next move will depend upon his current move.
Yeah, so that's the game, multi-agent, that's the hard part. So it's actually this safe learning for autonomous vehicles is sort of the whatever holy grail. I mean, people are doing various things. It depends on what the other car is also doing. It's not your own car. So that's a hard problem. I mean, nobody will put I don't think anybody has put a autonomous car on in a regular traffic. They do under somewhat controlled environments. Only in California where roads and traffic is very predictable. And